Do you know what complex numbers are? Yes? Okay, so then this will go fast as well. So before I talk about complex numbers in general, let's talk about this little special number that we call the imaginary number or imaginary unit, okay? Which we represented by the symbol I. So to introduce why this is, why do we care about something like this, let me, I guess, begin with a little example. Let's keep recording. Yes. So let's see, simplify. And let's do square root of 4. And let's do square root of 36. And let's do square root of -9. And let me say, okay. Again, let's say, assume at this point that I have not mentioned to you what I is. So all you know right now are real numbers. Okay, let's say that all you know right now are real numbers, even though you probably already know what happens in part C. But just assume that you know real numbers. Okay, so what's the answer to A? Yes? 2. Good. So just to clarify, remember that's a symbol that we use for square root. So you just need a number. So when you square it, you get this guy inside. And this is, there are 2 possibilities at that point. So let's see, what are the square roots of 4? If I say it in words, if I tell you, give me a square root of 4, what should be your answer? 2 and -2. Square root is just a number, so that when you square it, you get the original one. So there are 2 possibilities here, 2 and -2, right? Now the positive one is called the principal square root. And when you use this symbol, this is called a radical symbol. What we are asking is, I want the principal square root of 4. Sometimes we just say square root of 4, but really what we're saying is the principal square root. Okay? That's why that is. Okay. So how about B? 6. Good. And how about C?
Assuming we don't know what I is, there will be no solution.
So all we say, since you know a little bit more, we just say this is not a real number. In other words, there is no square root. If you are only thinking about real numbers, you cannot make sense of square root of something negative. Why? Because what happens when you square a real number? It will always be positive or 0. If you square 0, you get 0. But if you square a non-zero number, regardless whether the number itself was positive or negative, the square will always be positive. You understand this? So there is no way that you can give me an answer here that is a real number. Because when you square that guy, you will get positive 9. You're not going to get 9. Yes? So you see something like this, then we say, well, you could say no solution, or, you know, if you are a little bit more optimistic, just say not a real number. I mean, you know, maybe something, but definitely it's not a real number. Okay? So, you know, this idea of I, we introduce it just to make sense of stuff like this. And why do you want to make sense of something like this? Because, you know, in mathematics, you always want to solve equations. We haven't talked about quadratic equations yet. But, you know, there is a very simple equation, square plus 1 equals 0, that we would like to make sense of this. We would like to have a solution for this equation. The problem with this equation is that if you're only thinking about real numbers, it doesn't have a solution. Okay? For example, this equation is equivalent to the statement x squared equals -1. Right?
Wasn't that the equation that for the imaginary numbers?
That's what I'm trying to say. That's the reason why we want to make sense of something like this. Okay? Because when you are here, you know, you want to make sense of this, but if you are only you know, concerned about real numbers, or if you only know real numbers, you cannot make sense of this statement. You would just say, oh, this doesn't make sense. There's no solution here. It's true, there's no real solution. But if you want to go further and make sense of this, then we need to introduce more numbers. We need to enlarge our perspective. Okay? And in general, this has been true in mathematics. For example, do you think people from the very beginning they knew fractions? Let's say when humans started to think and develop mathematics, what do you think was the first type of numbers that came out?
Integers.
The positive integers, like the counting numbers, 1, 2, 3, 4, 5. You just wanted to count stuff. But then, you know, they started to make trades and so on, and then, you know, you owe me something, you owe me this, you owe me that. How do you represent owing something? Okay, then that's where negative numbers came into play. So now you have the positive integers, now you have So the natural numbers, which are the positive guys, then you have the negative version together with the zero. Zero is a different discussion. Some people believe that zero was a natural number, other people don't. But anyways, all those numbers together with zero, the integers came in. And you can think of this as follows. You can think of this in terms of equation. Like the natural numbers, they come because you want to solve an equation of this form. X minus something equals to zero. You can make sense of this, assuming that A is positive. If you know natural numbers, you can solve this. But the moment that you say X plus A equals zero, if you only know natural numbers, this doesn't have a solution. But let me give you something concrete. If you have this, you can solve it if you only know natural numbers. Yes? Because you get X equal to. Now, if you only know natural numbers, like counting numbers, can you solve the second equation that I wrote? No. So if you want to make sense of this equation, what do you need to do? You need to enlarge your number system. Okay? So now all of a sudden you need to say, oh, I need to allow or make sense of what a negative number is, and then you can make sense of this equation. And for a long time, people were fine with it. But then at some point, people wanted to start dividing stuff. Like, here is an apple, and then two people, they're hungry, one apple. What do? You want to start splitting stuff. Okay? It's taking a unit and then splitting that. So how do you make sense of that? You can talk about an equation. For example, think about this. Two people want to eat one apple. Or let me say this. Two people for one apple. Okay. If you only know integers, can you make sense of this equation? If you only know, 1, 2, 3, 4, and the negative, can you find a solution to this equation? No. So once again, you need to allow yourself more numbers. Okay? And notice that the way I'm doing it, every number system is including the previous one. Like the integers is a combination of these two, so it contains an alphabet, right? Now here we introduce the rational numbers, right, which are all the fractions. So here the solution, you can make sense of this with natural numbers. Here you can make sense of this with the integers. Then we introduce the rationals. Actually, up to very recent, when I say very recent, is up to the Greeks and so on. These all people knew. But then something strange happened. So as you know, there are numbers that are not rational. So a rational number is a number that can be written as a fraction. Okay? But for example, here is something very, very easy to see. They had a square. They started to divide land. Or look at this floor. There is a square tile here, right? So it's a square. Let's say for the sake of argument that this square has side 1. Okay? And then, typically, since they only knew rationals, typically, they were dividing stuff like this. Like 1/2, etc. But then, one guy came and said, no, I don't want that. I want to do this. I don't want a rectangular shape. I want a triangular shape. And it can be done. This is something that exists, right? You cannot deny that this side exists. You understand this? We're not making this up. Well, then, if you only know rational up to rational numbers, the rational numbers include all of these guys. That's all they knew. It should be a rational number, right? What's the length of this diagonal? They knew Pythagorean theorem at that point. This is from the Greeks. So who can tell me so this is a right triangle, right? What's the length of this diagonal? The square root of 2. What's the problem with square root of 2?
It's not rational.
The problem is that they only knew rational numbers, and this was an issue because this number cannot be written as a fraction. That's actually a little, a small little challenge for you. So, little challenge. Argue that square root of 2 is not rational. So try to see if you can prove this. In other words, that you cannot write this as a fraction, as a quotient of 2 integers. Okay? And that was a big problem because all of a sudden they say, oh, well, there are other numbers out there that they cannot be written as a fraction. So there are more numbers than the one that we know up to now. And then k pi, which is found by looking at a circle, you measure the circumference, divided by the radius, you always get the same thing, right? Regardless of how big the circle is. Turns out that number is not rational, and many others. Okay? So then we needed to enlarge a number system once again, and what we did was there is another family here which are called the irrational numbers. Let me put it here. Typically we use like an I or something for that. Or not rational numbers, okay? So the irrational numbers, those are numbers that exist, but they cannot be written as a fraction. Okay? Yes, square root of any prime number is irrational. And then what we do is we put these two guys together, and that's how the real numbers come to be. And for a long time, people were happy with this. This is all we need, real numbers. But then again, as you can see, most of the time it came because we wanted to solve equations, and so we were forced to kind of enlarge a number system. This is a little bit. Well, actually, you can think of this as another equation, right? So what's the equation that you can solve in here? So if we call this one x, so what was the equation? X squared equals 2, right? So that's the equation. We wanted to make sense of that equation. And what's more, we know this has a solution. It's this side. And it's something that exists. We're not making that up. Something real, okay? But here, on the rationals, you cannot solve it. So you have to accept that there are more stuff, even if you don't know there are more stuff out there. Okay? So, but it's real, so you put them together, and the things that you see concretely, the irrational ones, is more strange. Put them together, you get the real numbers. But again, an equation. But then all of a sudden, what if you want to make sense of this equation? Now, the thing is that, why do we call it imaginary? Because, it's not really as concrete as this one. This one, you do know that this is something real that exists, something concrete. That, this existence of the solution of this is not something really concrete that you can show me right now, like in nature or something like that, okay? So we just decided to call it imaginary, okay? Because we want to be able to solve things like this. And it turns out that it works, okay? And why not? So as we're about to introduce what this guy is and all the operations, we're saying that these are numbers. So when you have numbers, you should be able to add, subtract, multiply, divide, and all of that business, okay? So to find roots, that's a different story. Once you learn trigonometry, you will learn how to find roots of complex numbers, okay? Like square root, cube roots, and so on. Because that's a little bit more subtle than just real numbers. But anyways, complex numbers are important. And for us in mathematics, is at least they allow us to solve any polynomial equation. In fact, you're going to see later, there is a theorem called fundamental theorem of algebra that says that any polynomial has a root if you allow yourself complex solutions. Because if you don't, then this one doesn't have a root. The root is a zero of a polynomial, something that makes it zero. Okay? All right. So, well, I guess I'm going to leave this discussion here. This is a side tool. And try to see, if you like to play with mathematical reasoning, try to see if you can show the square root of 2 is not a rational number. It's a nice little argument that you can do, but it requires other type of thinking. Okay? If you want, then you can ask me later if you're curious. Okay, so the point is that we want to make sense of something like this, square root of -9. Okay, so for that we are going to introduce this little number. So definition. So we define the square root of -1. So when you do the square root of -1, as you know, for real numbers it doesn't make sense. So we're going to define this by this symbol, by the symbol I. By the way, this is only done like in the last 50 years or so. If you take a book from the 60s, you're not going to see I. You will see square root of -1 written everywhere. Okay, but it's just that it was very tedious to type this because at that point, they were even using the typing machine and so on. It was very tedious to write this, so they say, well, let's just give it something else, and then they switched to the same. Okay, so we define the square root of -1 to be I. So it works. So I is a symbol, so that when you square it, what do we get? So remember, this stands for, this is something, so when you square it, you're supposed to get the stuff inside, right? I mean, we want to mimic the same thing that we're doing up here. Why is this 2? Because when you square it, you get the stuff inside, right? Why is this 6? Because when you square it, you get the stuff inside. Well, if I declare that this is I, what happens if I square I? You should get -1, right? So this right here is the defining property of this symbol. So I is a symbol, So when you square it, you get -1. Do you understand this? Okay, we call it the imaginary unit. So we call it the imaginary unit. And this is used a lot, for example, in physics. Within complex numbers, if you want to explain the behavior, I don't know much physics, but if you want to explain the behavior of electricity, real numbers are not enough. Complex numbers are needed. And electricity is something that we are all enjoying every day, right? So it's useful, not just for mathematical purposes, but also for application. Oh, okay, so we call it the imaginary unit. And then the moment that we have this, we can enlarge our perspective, because then, then a number of the form a times I, where a is a real number. Now that I have this I can just multiply I by any real number, and we get what we call an imaginary number. Where a is a real number, is called an imaginary number. So we can make sense of 3i, 4i, 2i, -3i, etc. And then we can take advantage of this to make sense of square root of negative numbers. So for a positive, then the square root of -a, we define this to be the square root of a times the square root of -1. Remember, negative a is a times -1. Okay? So you split it, and then this is just square root of a times I. So moral of the story, when you have the square root of a negative, what you can do is get rid of the negative and put an I outside. Okay? So you know that you're getting an imaginary number as a result. So for example, if we want to do square root of -9, according to this property, this is just square root of 9 times I. But as you know, square root of 9 is 3. So that equals to 3i. It's an imaginary number, and it's a number so that when you square it, you will get -9. So let's check. So indeed, if I take 3i and I square it, as you know, this is the same thing as 3 squared times I squared. When you square a product, you distribute the exponent. So 3 squared is 9, and what's I squared? -1, and 9 times -1 is -9, as expected. Okay? So when you have square root with a negative inside, basically, just get rid of the negative, but then you need to pay a price. What's the price? You have to put an I multiplying the square root outside the square root. Okay? And then you simplify this as much as you can. Okay. Questions about what I is and how to make sense of negative square roots? So if you see a negative square root, we no longer say it's not a real number. Okay? Now we know a little bit more. If the problem only cares about real numbers, then you say there is no real solution. But if the problem doesn't say anything, don't assume that they only want real solutions. Okay? Let's see. Examples. Simplify. Let's do square root of -49. And let's do square root of -75. So, what's the answer to the first one? 79. Very good. So, again, the negative is just, we give you the I, and then square root of 49 is 7. All right, how about B? How do we do this one? Yes.
You want me to choose the answer?
Okay, give me the answer first, and then you tell me how you got to it.
5 square root of 5i.
5 square root of 5i.
I believe so.
You believe so. Think about it again.
Is it
Yes.
5i square root of 3?
Okay, good. So inside square root, you have a 3. So let's see, let's do it slowly. So first of all, everybody understand that the answer has to have an I, right? Because the negative.
I for some reason believe that 5 times 25 was 75.
But no. Okay. Okay, good. So this would be, let's do it slowly. So a 75i, right? Square root of 75, and then we put the I outside. Now the question is, how do we simplify square root of 75? Now, in the examples above, we have here what we call a perfect square, like something that can be written as something square, so you can easily cancel and no square root left over. However, 75 is not a perfect square, right? There's no number whose square is 75, like integer. So what is it that you do? We factor the number, try to look for a perfect square that is a factor of 75. So how can you write 75 as a product that contains perfect square? And if you think about it, yes?
75 is equal to 25 times 3.
25 times 3. Good. So you can write it as 25 times 3. Why like this? I mean, in this case, you could also write it as, for example, what is it? 15 times 5, right? But that doesn't work. That doesn't help. Why? Because neither 15 nor 5 are perfect squares. So we want to write it as something that has a perfect square at least. And 25 happens to be a perfect square. 5 squared. So when you have this, that means you're allowed to take 5 perfect squares out of the radical by taking the square root, and whatever is not a perfect square stays inside the radical. Okay? So this becomes 5 square root of 3, and then I. As a good practice, we usually try to write the I at the end. Okay? But if you write, like your classmate mentioned earlier, 5i square root of 3, that's okay. All right, doesn't matter where you put it. But it's a good practice. We write at the end. However, see how I do this little thing down here for the radical, just to let you know that my radical stops here. So whatever comes after is not part of the radical. Because if you don't do that, if I write this, then you'll be like, okay, did you just forget to extend the line? Is the I inside or outside? If you don't like to do these things at the end of the radical, then you probably should be writing this just to emphasize that the I is outside the radical. Okay? So that's why you may see this somewhere, just to make it clear that I is not inside. But I like to denote when my radical stops. Okay, good. Questions on simplifying square roots with negatives inside? All right. So before we move on to complex, because these are imaginary numbers, then we have complex numbers. But before we go there, let's keep exploring I a little bit. In particular, I want to discuss powers of I. Do you know the behavior of powers of I? So by powers, I mean when you raise I to a certain power. If I ask you, what's I to a 343? How do you do something like this? Okay, so that's what it means. So let's explore this idea. So powers of I. So powers of I. And one of the questions, let me just pose the question here. So one thing that we would like to explore is, okay, is there a reasonable way to compute something like this? Of course, you can sit there and multiply I 343 times. But nobody wants to do that, right? So the question is, can we get here in a quick manner? Is there some sort of pattern or formula or behavior that powers of I exhibit? Okay, so let's look at that a little bit deeper. And to understand this, let's just do some experiments. Let's start writing down powers of I until hopefully we get some sort of pattern, and then we can generalize it. Okay, so let's begin. I'm gonna just look at positive exponents because negative is just turned into a fraction, right? Okay, so let's see. Let's just do some. Let's see. I to a 0. Let's see. I to a 0. What's I to a 0? 1. Good. Remember, any number to a 0 power by definition is equal to 1. Okay. I to the 1. I. Okay. What's I squared?
-1.
-1. Now, what is I cubed? -I. Very good. So you either sit down and multiply 3 times, or just realize that to get this line, just look at the previous one and multiply both sides by I, right? If you multiply I squared times I, you get I cubed, and therefore negative 1 times I is negative I. As you can quickly get this. Understand this? Okay, now what's I to the 4?
1.
Does everybody understand that is equal to positive 1? So I'm going to put it here. So I to the 4 equals 1. What's I to the 5? I to the 6.
Negative 1.
I to the 7.
Negative 5.
Does everybody see what's going on? It appears that these values are consistently repeating themselves. Let's try one more time. So what's I to the 8?
1.
1. Make sure that you convince yourself that it is 1. Okay? You can get it by multiplying the previous line. Like here, and multiply both sides by I. Okay? And so over here, you're going to have negative I squared, which is minus 1. Give you positive 1. Okay? What's I to the 9? Again, multiply the previous line, both sides by I, right? So you get I to the 9 to the left, to the right, you get 1 times I, so it's just I, okay? I to the 10, negative 1, I to the 11, negative I. And hopefully you agree that, we are in this endless cycle. So it looks like we'll always get, no matter what the power is, we will always get one of these 4 values. Okay? The question is, how do you identify this? Okay? So notice that, for example, in the first row, these are all the cases in which we're getting 1s. Right? For example, what will be another guy in this row? What power would be here? 12. What will be the next power? 16. Right? What do all of those guys have in common? And multiples of 4. Good. So I would like to rephrase that pretty soon, but let's keep it like that. Multiples of 4. So 0, 4, 8, 12, 16, they are all multiples of 4. Yes? Let's look at the next row. All of these guys are giving me I. So what will be the next guy here?
13.
13. Yes? The next one?
17.
17. So you do plus 4, right? Get the next one. They will all give you I. What do they all have in common? Those numbers.
They're all adding 4. Well, for everyone, yeah, the 4 power.
So what do the powers in this second row have in common? How would you describe them all in one shot? For example, the ones on top, we said they are even numbers. They are multiples of 4, right? You put them all together in that sentence. How about 1, 5, 9, 13, 17? How do you put these guys together? What do they have in common?
Plus 1.
Good, right? They happen to be one more than a multiple of 4, right? In other words, these guys, they can all be written as, they satisfy this general pattern, 4 times n, for some n. They are multiples of 4, yes? Where n is an integer. Now, in the second row, what patterns do they have? They have the form 4 times something plus 1. Yes? Does everybody see this? Okay. Now, in the next row, what's the pattern? So what are the ones that will give you negative 1?
4 times 10 plus 2.
They are 2 plus the multiple of 4. Yes? So they have the form, all of those numbers, these guys, they have the form 4 times n plus 2. And then how about the last row? What's the pattern?
3 more than a multiple of 4.
3 more than a multiple of 4. 4 times n plus 3. Notice that if you wanted to write and then what about 4n plus 4? Well, 4n plus 4, that's just 5. That is just, you can factor out your 4 and then you get 4 times n plus 1. So that goes back to this category, 4 times something. Do you understand what I'm saying? So, what is another way of talking about these numbers? For example, if I ask you 343, I wanted to answer this question. So the point is, given a power, what you want to know is in which of these 4 categories it lands, right? Once you know in what category it lands, then you know the answer. For example, the first category, the answer will be 1. The second case will be I, negative 1, or negative I. Yes? So we need to have a quick way of figuring out what category it lands. So 343, how do you figure out which one is it? In other words, yes?
I don't think this method I'm gonna say is exactly what you're looking for, but what I do is I divide the power by 4 and take the remainder.
That's exactly what it is. So when you say this, so keep in mind that 4n is the same thing as 4n plus 0, right? So if you can write a number like this, what this means that when you divide by 4, remember, when you divide by 4, there are 4 possibilities in the remainder. You either get remainder 0, meaning the division was exact, or remainder 1, 2, or 3. Okay? And the remainder are exactly these guys right here. In other words, a number has remainder 2 if it can be written in the form when divided by 4, if it can be written as 4 times an integer plus 2. Okay? This is unique. If you can write like this, you cannot write it in any other way. So these guys are the remainders. So I just point it out to quickly spot in what situation you are. Just take your number, divide it by 4, and look at the remainder. Okay? And then you will know in one of these 4. In other words, if you want to know powers of I, this is really what you need right here. Because right here you have your remainder. Remainder 0, remainder 1, remainder 2, remainder 2. Okay? And this is pretty easy to understand what the values are. Okay? So let me write down the theorem. The theorem. So let n be any non-negative integer then any integer can be divided by 4, then it can be divided by 4 and r is its remainder. Okay, now this number r is either a 0, a 1, a 2, or a 3. Do you understand this? Yes? Okay, so and r is remainder. So then what we just observed, which is actually the case in general, is that if you want to do I to the n, you can just replace this by I to the r. Okay? So you, no matter what power you have, you divide by 4, look at the remainder, and then you reduce this problem to 1 with 4. And then this one, you just figure out what it is. Okay? But if it's 0, 1, or 2, it's easy to see. And 3, well, just remember, you just multiply I 3 times, or you take this, multiply by I, you know, the negative I. Okay? So, and the proof of this theorem is basically the analysis that we just did above. Okay? So we see this pattern over and over. So if you wanted to do I to the 343, then what we need to do is stop a second, divide by 4. So let's divide 343 by 4. We do a little division. So what is this? What's the closest multiple of 4? So 32. Yes, 32. We put an 8. That's a 32. That's a 2. And the 23 down. Then this is 20, so that's a 5. So it's 20. We get 3 and we stop. We're doing integer division. So what this means is that 4 fits into this number 85 times, and then there are 3 little items left over. Okay? So what we are saying here is this means that 343 can be written as 4 times 85 plus 3. Okay? In other words, a remainder is 3. So this guy here is the remainder. I mean, I'm assuming that you're fine with long division. Are you okay with long division? Okay, so 3 is a remainder. So according to our theorem, this is the same thing as I cube. Okay, instead of worrying about 343, we just worry about the remainder, which is 3. And what do we know about I cube? What is this? Negative I. Okay, questions? All right, good. So you some little examples and then go to the next one. All right, so let's do I to the 38. Let's do I to the 101. I to 230. Again, just doing this just to give you confidence in the computation, just to make sure that you are okay doing the long division and all of that. So compute all of these powers. Right, number one, what do you guys get?
-1.
-1, okay? So what's the remainder when you divide by 38? 2. So, when the numbers are small, just see if you can find a quick multiple of 4. That's the closest multiple of 4 to a number. So you see that 38 is 36 plus 2, right? 36 is 9 times 4. So that's how you can quickly see that the remainder is 2, which is -1. If you don't see it, then divide, okay? But when the numbers are small, you can quickly do it. All right, about number 2, what's the remainder? Remainder 1, because 100 is the closest multiple, right? So 100 plus 1. So this is I, which is I. Okay, good. All right, so how about number 3? What's the remainder in 230? 2? So 228. When the last two numbers, so a quick divisibility by 4 is if the last two digits are a multiple of 4, then the number is a multiple of 4, right? So 228, 28 is a multiple of 4, so 228 is a multiple of 4. So you can do 228 plus 2, so the remainder is 2. Good. It's -1. Again, if you don't see it, you can just, do the little division. This would be, what is this? 5, 20, 3, 7, 28, and then you get your remainder 2. Okay? Okay, about this one? Let's see, using the trick that I just told you. What's the closest multiple of 4 for this one?
32.
So, focus on the last two digits. What should we make this guy be? 32, so 1,132, right? That's the closest multiple of 4. Therefore, what's the remainder? How much are we missing?
3.
3 more, right? To get to 35, from 32 to 35. So if you divide, you should get remainder 3.
-I.
So you get -I. Did you understand this? So again, let me just do the division. So you see I'm not doing voodoo magic here. So 2 plus 8 plus 3. Bring this guy down. What is this? 8, 32, 15, and then what is this? 3, 12, and we get a remainder 3. Okay? So if you do 4 times 283, you should get 1,132. Okay? And then plus 3, they give you. Okay. And how about number 5? So what's the remainder? The remainder is 0, right? 64 is a multiple of 4. What is it? 15? No. 16. 16 times 4. Okay. Questions about finding powers of I? Okay. All right. So we have this. So now that we know what an imaginary number is, then we can talk about, why should we keep it like this? Remember, we always like, if you think about this kind of development of the number systems, if you will, we always, whenever we make it larger, we try to make it in such a way that the new system contains the previous one. So every natural number sits inside the integers, right? You can think of a natural number as an integer. Every integer sits inside the rational. Just write them over 1. Okay? Now, the rational don't sit inside the rational. The irrational are not part of the rational. They're actually two different words. What we did was we put them together and create the reals, just to get something that contains both of these guys. Okay? So every time a new system will contain the previous one, but we try to make it that way. So now we're introducing these imaginary numbers, but the imaginary numbers right now have no relation with the real numbers. They are two words apart, okay? So now we're gonna put them together, we're gonna enlarge the imaginary number, we're gonna get something called complex numbers, so that we contain, the complex numbers are gonna contain real numbers as a subset, okay? Every real number can be considered as a complex number with imaginary part equal to 0, okay? So it means plain this. And you know, there is a reason for this. So we want to contain all the previous numbers that we have, but also there is a graphical reason, if you will, slightly geometric reason for us to define complex numbers. And let me actually do that. So real numbers. So real numbers. How do we represent graphically a real number? If I give you a number 3, and I ask you, give me a picture of the number 3, what do you do?
The number line.
We draw a number line, right? I want a picture, a graphical representation. I mean, okay, that's a graphical representation, but that's not what it means, okay? Like a graph. So the point is that there is something that we call a number line or the real line, right? It's a line that stands both ends non-stop. Then we declare one point here, we declare it to be the middle. We say this is 0, and then, you know, we declare all of this is, you know, you declare this. So we declare that this means 1, therefore 2, 3, and then, you know, all of these things are immediately set the moment that you declare what 1 is, etc. And then if I give you a real number, let's say the number 3, you just go and then you put a dot in its place on the number line. If I give you the number 1/2, then you go and you put a place in the line. And it's guaranteed that every single real number has a place in this line, right? The real numbers are what we call a well-ordered set. So given any two real numbers, you can compare them. You can always say when one number is less than another one. How do you know this? How can you say that one number is less than another one? Yes?
It's on the left side.
Very good. When you put them on the real line, whoever is to the left, whoever is the leftmost number, that's the smallest one. Okay? But we can do this. That's called a well-ordered set. But understand that also the other way around works. Any point on this line is a real number. In other words, this line is already filled. There's no free spot here. Do you understand this? Okay. Now we just introduce a new symbol, namely I. Where do we put it? There's no place for that guy in here. Everything is taken. So what do we do with I? Yes?
We make a different number line vertically.
Very good. So we draw another line. I mean, this one is called the real line. We call this one the real line, and it's completely filled. Then for imaginary numbers, then we just draw another line, and we call it the imaginary line. Okay? Now, because I'm doing it by itself, I could do it horizontally if I like. The idea is I want to put the two together. So if one is horizontal, I'm gonna just place the other one vertical. So let me put it like this just to get you used to it. But since it's just one line, it doesn't really matter how you put it. Okay? So we do the same thing. So we declare this is the middle, this is 0. Okay, let me make it so I matching some other things here. So let's say that this is 0, then we declare that this is 1, this unit is 1, but instead of 1, we call that number, we call that I. And then what would be this one?
2i.
That would be 2i, and so on. In other words, this is just a copy of the previous line, but you just put I next to these guys, okay? Any number here, just stick an I next to it, and then you get your imaginary line. So negative I, negative 2i, and so on. So if I ask you I, okay, here it is. Negative 2i, here it is, and so on, okay? So this is called the imaginary line. So what we like to do is, okay, we go ahead and we put the two lines together, okay? So here we have our real line. This is 0. And then right here, we put our imaginary line, okay? So as a real line. Here we put the imaginary line, this is the imaginary line. And for example, here you're gonna have numbers like 1, 2. Here you're gonna have numbers like I, like 2I, and so on. Okay, and that's fine. So every real number will go in the real line. Every imaginary number will go in the imaginary line. But all of a sudden, we went from a one-dimensional world. So here's the real line. This is a one-dimensional thing. So everything is filled. There is no space for anything else. But the moment that we introduce a new line, we jump. We went from 1 to 2 dimensions, right? Now, this blue line is entirely filled. Do you understand this? But we have a bunch of leftover spaces. How about things over here? Things over here, and here, and here. Why are we going to, ignore those spaces? So numbers that go here, we call them complex numbers. So for example, now we can do the following. Okay, let's start mixing things together, and let's say this point over here now is going to have a meaning for us. Okay, so this point has a real component and an imaginary component, right? So the way that we talk about this point is we write it as 2 plus 2i. And this is an example of what we call a complex number. And this is called the complex plane. Okay? This is called the complex plane. And now all of a sudden, every single point on this plane can be thought of as a complex number. How? Any point that you give me, you project it down to the real line, you get a real number. You're projecting to the imaginary line, you get an imaginary number, and then combination of the two is what makes up the complex number. Do you understand this? So a complex number is something that looks like this. A number plus another number times I. Now, this first number that doesn't have any I next to it, we call it the real part of the complex number, as you probably can observe. And this number, this other number over here, without the I, this number is called the imaginary part. Okay? So the real part of this complex number is 2, the imaginary part is 2. Okay? Let me write these things down. So definition. A complex number is an expression of the form a plus bi, where a, b are real numbers. Okay, a and b are actually real numbers. And I is that symbol that when you square, you get -1. Okay? So whenever you see something like this, then we are in the presence of a complex number. And these guys have names. A is called the real part, and B is called the imaginary part. Okay? So A is called the real part. And sometimes we write it as like this. So the real part of A plus BI is just A. Okay? And B, I'm not going to be writing that, but you may see this if you read online or see other sources. And B is called the imaginary part. And then it should be clear why we call them like that, okay? If you now think about what I just showed you in the picture. This is, by the way, how you geometrically represent a complex number. So it's called the imaginary part. And sometimes we write it like this. I am A plus BI, this is B. So understand that both real and imaginary part are actually real numbers, okay? It's just that the real part means there's no I next to this guy, imaginary part means there's an I next to this guy, okay? And now with this definition, every real number is also a complex number. It's just that the imaginary part is 0, right? Because any real number will sit on this line having an imaginary part 0. Similarly, an imaginary number is also a complex number with real part 0, right? So, any real number can be thought of as a complex number with imaginary part. With imaginary part equal to 0. So in other words, I don't know, the number 7 is a real number, but you can write it as 7 plus 0i. So if you want to think about it as just a real number, you just think about the number 7. But if you want to think about it as a complex number, then you will represent it like this. Okay? For whatever reason. But those two things are the same. Okay. Also, I want to remark the complex number. So I'm going to give it as an example, but actually, let me write it in general. So if you write a plus negative b times I, right, let's say that the imaginary part is a negative number. Okay? If this happens, this is the formality of how you should write it because of the definition. But as a shorthand notation, as usual, we will write this as a minus bi. Okay? So what I mean here is if you see 2 minus 3i, what this really means is 2 plus negative 3 times I. Okay? It's just that we don't like to be writing this around all the time, so we have this. It's understood that this means that negative 3, including the sign, is the imaginary part. Okay? Okay. Questions about what a complex number is? Yes?
So if any real number can be thought of as a complex number with the imaginary part equal to 0, could any imaginary number be thought of as a complex number with a real part?
Yes, exactly. I said it, but I didn't write it. But because typically when you see the I already, we don't even think about imaginary numbers anymore. We just say complex, right? But the interesting thing is that if you don't see an I, you can also say it's complex, but just enforcing the fact that the imaginary part is 0. But indeed, every imaginary number is also a complex number, okay, with real parts. Are we okay with this definition? All right, so we're calling these things numbers. So that means that we should be able to do arithmetic operations with them. We should be able to add, subtract, multiply, divide. Okay? First three things are straightforward. The last one, the division part, is the one that may require a little bit of discussion. Okay? So I'm going to show you via examples. Okay? So how do we add complex numbers? What do you think? What would you do? Let's see.
Add A and B separately.
Exactly. So real part with real part, imaginary part with imaginary part. Okay? So just combining like terms. That's how you add complex numbers. Same thing how you subtract complex numbers. Okay? Multiplication of complex numbers, it's not a problem. Just distributive property. Distribute and then remember I squared is negative 1. The question is how we divide. Okay? So let's do some examples so we can get to the division quickly. So arithmetic operations. So arithmetic operations, complex numbers. So first, let's do addition, subtraction. I'm just gonna write here the definition, but the definition is that if you have a plus bi plus or minus, I'm gonna write the two operations at once. C plus di, let's say that you have two complex numbers and you want to, okay, let me just do it. And you want to add them, you just do real part with real part, and then imaginary part with imaginary part. That's all, combine like terms, okay? And then similarly with the difference. So if you're doing a plus bi minus c plus di, you subtract real part with real part and imaginary part with imaginary part, okay? But again, you just combine like terms. So you just ignore the parentheses and start combining things. Numbers with numbers, I with I's. Okay? That's pretty much what it is. So every time that you do operation with complex number, the upshot is that you want to write the answer in standard form. The standard form is a plus bi. So a number plus a number times I. So you don't stop until you get that form. Okay? Like here, it's the number plus the number times I. That's the idea. So let's see. Let's do some examples. How about 3 plus 5i minus negative 9 plus 3i. And then let's do negative 5 plus I plus 2 minus 5i. Okay, so again, just the easy thing here is just to get rid of parentheses. So this is 3 plus 5i. Now be careful, there's a negative. So I was going to make it plus 9 minus 3i. And then just combine like terms, okay? Then we're going to say it out loud with the property. But, it's easier just to do this. All right, so 3 plus 9, that's a 12. And then 5i minus 3i, that's 2i. Okay? So now let's do it following the property, if you will. So we're subtracting, so we're supposed to subtract the two real parts. So 3 minus 9, that's 3 plus 9, gives you 12. And subtract the imaginary part. So 5 minus 3, gives you 2. Okay? All right. So what about number 2? What's the answer?
-3 minus 4i.
So negative 3 minus 4i. Good. Does everybody understand this? Let's combine the numbers. Combine the i's. All right. Questions about addition and subtraction? I mean, addition and subtraction is really not complicated. No more work. Okay, so that's addition and subtraction, then multiplication. So number 2. Multiplication. Here the idea is, I could give you a formula. It's just that the formula is going to be super strange and big. There is no reason to memorize that formula. Okay, it's easier to just follow the distributive property. Like here, I gave you this formula for addition. I could give you a formula for multiplication, but it's going to be very long, and there is no point in memorizing that formula. So instead, the idea is that when you multiply the complex number, you just use the distributive property. Okay, so idea. Use distributive property. Distributive property, and the fact that when you distribute, at some point you may get I squared popping up. Just remember that when this happens, it turns into a -1. Okay? So use distributive property and use the fact that I squared equals -1. And then write the answer in standard form, which is A plus B. Okay? All right, so let's do examples. So you can see that. Let's do 4 minus 2i times 3 plus 6i. And then let's do 2 plus 7i times 2 minus 7i. Okay, let me I'm going to give you 2 minutes to do it. Let me do it together. We're almost done. But we have to do this. Yes.
When you times multiply two i's together, do you put the square the?
So remember, I times I is I squared.
I square.
Yeah. And then use the fact that I squared is. Do you know what the distributive property is? Okay. Okay. Anybody has an answer for number 1? Yes.
24 plus 18i.
Everybody getting the same thing? Yes. Are you talking about number 1, number 2? So what did you get? So 24 plus 18i. Is everybody getting that? Okay, so let's see. Let's do it just in case. So remember, distributive property. What do I mean by that? It means take the first guy. So that's how you multiply things like this. So take the first guy and multiply it by everything else in the next parenthesis. Okay? And then go to the next one and repeat. So if you had here 20 terms, you do the same thing. Okay? Of course, in that case, you distribute this one instead of the other one. You usually distribute the one that has less, so you minimize the number of steps. But the idea is take the first guy, distribute it, then move to the next one and repeat. And then you combine. Okay, so you distribute the 4. So we get 4 times 3, that's 12, plus 24i. Yes? And go to the next one and repeat. So negative 2i times 3, that's negative 6i. Negative 2i times 6i is going to be negative 12i squared. So now no more parentheses, we just combine like terms. Now remember, I squared is negative 1, so this is really a positive 12, right? So let's write that down. So we get 12. I can already combine these two guys. So what is that? That's 18i. And then negative 12 times negative 1, that's positive 12. So now we can do 12 plus 12. That's 24. Are you okay? Okay, good. And then how about number 2?
53.
53. Everybody getting 53? Okay, good. Let's see, who can tell me what's a quick way of doing this? Yes?
Just multiply 2 times 2 and then 7, 9 times 7, 9. Since they're conjugate pairs, the imaginary numbers, what's the word? They get rid of each other.
Okay, why?
Because one becomes positive and the other becomes negative, so they cancel out.
They cancel out. Okay, good. Or if you think about factoring, this is gonna give you the difference of squares. So do you know what I'm talking about? Because the next thing that we're going to discuss is factoring. So I want to make sure that you remember these things. So if you have something like this, a squared minus b squared, we call this a difference of squares. Okay? It's clear what we call it. It's a difference of two squares, right? But this factors in a specific way. How does this factor?
A plus b times a minus b.
A plus b times a minus b. You know it works. You can write this as a product. So if you distribute this by playing this game that I did here, you will see that the AB term will cancel out and you will end up with a squared minus b squared. Okay? Now these things, notice that these two expressions are very similar. The point is, the thing is that one is plus, the other one has a minus. We call these conjugate pairs, as your classmate was pointing out. So every time that you have a product of two conjugates, you will always get this, a difference of squares. Okay? The first one squared minus the second one squared. And that is actually what's happening here. These two guys, we say they are conjugate to each other. So this is the notion of the conjugate of a complex number. It's another complex number. We have the same real part, but the imaginary part, you change the sign. If this one is positive imaginary part, then you make it negative. And if it's negative, you make it positive. Okay? Every time that you multiply a complex number with its conjugate, this is the difference of squares. So this is going to give you 2 squared minus 7i squared. Right? The difference of squares. But then when you simplify this, you see that this is going to be 4 plus 49. Right? Or let me express the fact that this has a form 2 squared plus 7 squared. Because I'm going to come back to this in a second. Giving you the 53. Yes? Okay. Let me make an observation here. Here we multiply two complex numbers, and what type of number do we obtain as a result?
Complex.
A complex number. Now here we multiply two complex numbers, but what type of number do we obtain as a result?
Real.
We actually obtain a real number. Yes, notice how the I is gone. So keep in mind that when you have a complex number, if you want to get rid of the I part, if you want to get rid of the complex behavior, one trick could be multiply by its conjugate. Because every time that you multiply a complex number by its conjugate, the result will be a real number. The I will be gone. Why? Because you get the difference of squares, then here you have your I squared, which turns into a -1, and then the I disappears. Okay? So we're gonna take advantage of that idea to define division of complex numbers. Okay? As you're about to see. So let me write that down. So remark, or I guess definition, the conjugate of the complex number a plus bi is, what's the conjugate of a plus bi?
A minus bi.
A minus bi. And by the way, many times we like to use the letter z or w to denote complex numbers. So let me use that. So, and then we have a notation for the conjugate. That's the reason why I'm putting a letter here. So typically we use a bar to denote conjugate. So the conjugate of z, we write it like this. So we put whatever symbol we're using for a complex number, and then we put a bar on top. If you don't have a symbol, you just put the bar on top of the entire thing. Okay? And that just means find the conjugate of whatever this complex number is. Which means change the sign of the imaginary part. Okay? All right. So the conjugate of a complex number, a plus bi, is a minus bi. And then the theorem is, or the remark, I mean, it's just a tiny little observation, is that if you do, let's say that z is equal to a plus bi, then c bar is a minus bi. So when you do z times z bar, in other words, a plus bi times a minus bi, what is this? This is a squared plus b squared. Okay? And the interesting thing here is that this is now a real number. So you can get a real number out of a complex number by multiplying it by its conjugate. Okay? That's the observation here. And it's always the real part squared plus the imaginary part squared. Okay? All right. Okay? So we're going to take advantage of this now to define division. So we understand how to divide complex numbers. So questions on this? Okay. Division, so that's number 4. So division. Remember, the idea is that when you divide two complex numbers, you want to do something reasonable. Or when you do operation with two complex numbers, you want to do something reasonable that makes sense, and then make sure that you can write your answer in the standard form a plus bi. That's really what it boils down to. So let me first do it as follows. Let's first divide. I'm going to show you with an example, and then I guess you can see the general idea. So as an example, let's divide 2 plus, I don't know, let's say 2 plus 7i divided by 4. In other words, let's divide a complex number by a real number. Remember, real numbers can be considered as complex numbers, right? So you can write the division symbol, but typically we like to write like this as a fraction. Okay? So 2 plus 7i divided by 4. Remember, our job here is to write this in standard form, a plus bi. So what can we do here? What's a reasonable thing that you can do? Yes?
Split up so that's 2 over 4 plus 7i over 4.
Very good. So remember, when you have a fraction, on top you have a sum or a difference, and then in the bottom you have one thing. You can always split this as a sum or difference of two fractions with the same denominators. So you can write this as 2 over 4 plus 7i over 4. Do you understand this? And now you can simplify. For example, this is the same thing as 1/2 plus 7 over 4 times i. And this fits the description of what we wanted, right? So this is a number plus another number times I. So we're done. Do you understand this? So the point is that dividing a complex number by a real number is very easy. Okay? So the question is, how do we divide now by a complex number? The strategy is, okay, let's turn that question into a question like this one. So let's try to make a real number pop up in the bottom. And how can we get a real number out of a complex number?
Multiply by the conjugate pair.
Multiply it by the conjugate. So what we do is, when you divide by a complex number, you multiply top and bottom by the conjugate of the denominator. Remember, you cannot just multiply the bottom. You need to do also the top, otherwise you're changing the number. You're changing the problem. Okay? But if you do top and bottom, you can always cancel. So, for example, let's say if we do, let's do 2 over 2 minus I. And then, as another example, let's do 2 minus I over 5 plus 3I. Okay? I'm going to do the easy one, and then I'm going to let you the harder one too for you. And then we do it together. Okay, so again, here I'm dividing a real number by a complex number, but again, whatever we're going to do, it doesn't matter what's going on in the top. This could be a complex number as well. That's it. So the point is that we have a complex number down here. I don't want this guy here. If I have a real number, it's easy. We know what to do. So we want to get rid of this I. How do we do that? Multiply top and bottom by the conjugate. Why that conjugate? Because we have this property that when you multiply a complex number with its conjugate, you get a real number as a result. Okay? So we do 2 over 2 minus I, and then what we do is we multiply top and bottom by 2 plus I, by 2 plus I, because this is the conjugate of this. Just change the sign, remember. You okay with this? All right, so now when you multiply, on top we get, well, whatever we get. So we get 4 plus 2I, but then in the bottom, remember, this is a product of conjugate. So what is this? That's 2 squared plus 1 squared. Real part squared plus imaginary part squared. The real part here is 2, the imaginary part here is 1. Do you understand this? Okay, so this is actually 4 plus 2I over 5. And now we put ourselves in a situation that is number 1. As you know, this is easy. How do we do this?
Turn into fractions.
So split and write it nicely, right? So in this case, there is nothing to simplify. So we write this as 4 over 5 plus 2 over 5i. Okay, you know, and the promise is, because this is the result of dividing 2 by 2 minus I, if you want to check your work, what you should do is multiply this result with 2 minus I, and we need to get 2. Okay, that's how you can verify with the correct or not. So you can give you that as a homework to try if you want. Okay, so go ahead and do number 3. Yes.
I'm a little confused. Wouldn't the I when you multiply it, wouldn't the I just cancel out?
Okay, where?
In
Down here? Yeah, that's why the I is gone. But remember, here you need to do distributive property. So if you don't want to use, so this right here is basically this this observation that we made here, that when you multiply 2 conjugates, you will always get this. But if you don't believe it, or if you don't want to use this, or if you don't remember it, then what you should do is understand that when we do this product, let me do it here on the side. So if you do 2 minus I times 2 plus I, so let's do it. What is this? So that's 2 times 2, that's 4. 2 times I, that's 2I. Negative I times 2, that's negative 2I. Negative I times I, that's negative I squared. Right? Now notice how these guys are gone because they are opposite. But then you get 4 minus, now I squared is negative 1. So you really get 4 plus 1 as expected. Right? The thing is that you don't want to be doing this every single time. So it's good to remember that when you do this, you will always get real part squared plus imaginary part squared. And then okay. All right, so do number 3. wait one more minute. Okay, anybody has an answer for number 3? Yes?
7 over 34 minus 11i over 34.
So 7 over 34 minus 11. So typically we like to write like this. Okay, is everybody getting the same thing? Okay, so let's see. Let's do it together. So very good. All right, so let's see. We do 2 minus I divided by 5 plus 3i. So what do we need to do? What's the first step?
Multiply by the conjugate.
Okay, so who can tell me what's the conjugate of the denominator?
5 minus 3i.
So, make sure that you multiply by the conjugate of the bottom. Don't do the conjugate of the top. You could do the conjugate of the top, it's just that it's not gonna do anything helpful for you, okay? You will be putting a real number on top, but that doesn't really help. Like you will be getting something like number 2, okay? That doesn't really help. Okay, so now we carry out the product on top, we just distribute. So that's 10 minus 6i minus 5i plus 3i squared. And then in the bottom is product of conjugate, so it's gonna be 25 plus 9, right? 5 squared plus 3 squared. All right, so now just simplify. So what is this? So this is really a negative 3, right? I squared negative 1, so it's a negative 3. 10 minus 3, 7. And then negative 6 minus 5, that's negative 11. Negative 11i over 34. And now we write this nicely. 7 over 34 minus 11 over 34i. Good. Okay, questions? Okay. Let me just do one more. What about something like this? Like, so let's say that it's a 3 over 2i. In other words, how do you divide by I? That's really the question. Could you say 3 over I? But you say 3 over 2i. So you can do the same thing, right? So what's the conjugate of 2i?
2i.
Negative 2i. You have to change the sign of the imaginary part, right? Negative 2i. But in this special case, you do it, it's gonna work. It's just that then if you multiply top and bottom by negative 2i, the 2's will cancel out anyways. So it will do the job only if you multiply top and bottom by I. Remember, the idea here is that you just want to get rid of this I down here. This is what we want to get rid of this I down here. You will get rid of it if you multiply by negative 2i, that's true. But you will also get rid of it if you multiply by I. So in this special case, if you want a little shortcut, will be instead of multiplying by the full conjugate, just multiply by I. The reason why it doesn't work above is because if you multiply this by I, you will just be transferring the I from here to here. Right? So you will get 5i minus 3. So you just be changing the I from one side to the next one, so that doesn't work. That's why you need the full conjugate to be able to get rid of the I in things like this. But when you have a purely imaginary number in the bottom, the conjugate is fine, but it's quicker if you just multiply top and bottom by I. Because then this becomes 3i over negative 2, right? Because I times I is negative 1, So that's just negative 3 half I. And you're done. You will get the same thing if you multiply by negative 2i top and bottom, but then you have to simplify the fraction at the end. That's all. So I just wanted to make that observation.